Welcome back to another solution from Engineering Mechanics. Problem set 2.4 and solution to 2.58 is a good problem. Don't get panicked by look at the diagram with so many bars. It is a regular octagon. 1, 2, 3, 4, 5, 6, 7, 8. 8 corners, regular one. Now, let me read out first the statement. By means of a turnbuckle, this is a turnbuckle A. This part from here to here is a bar. This part from here to here is connected to one end. From here to here is connected to the other end of the turnbuckle. If you rotate the turnbuckle clockwise, this bar means this part and this part will be tightened, means there will be some axial force developed across it, and we will consider it as P. A tensile force is produced in one of the radial bars. This is a radial bar, this is a radial bar, this is a radial, this is also radial, this is also radial, radial, because it is along the radius of a hanged regular octagon shown in figure O. Determine the forces produced in other bars of the system. Now, I have redrawn the diagram. Now, let this point is equal to B. Let this is equal to C, D, E, F, G. This point is H and this point is I. I started with B because this is given as A. Let this point is O. So, consider the point B. If you look at the BC part and BI part, BC and BI under contraction. If you tighten this turnbuckle, there will be a force developed across this bar. Let it be P. So, by tightening it, BC and BI, if you tighten it clockwise, BC and BI will try to contract. So let S1 is the axial force developed in BC, S2, S3, S4, S5, S6, S7, S8, which I have shown in a different diagram here. So S1 in BC and S8 in BI are acting towards the point. S1 is acting to this side and S8 is acting towards the point B. And P is acting towards this side. Alright. So let angle, I have shown in a larger diagram. Now let angle ODE is equal to angle OED is equal to alpha H. Now the question is how this angle is 45. This is 90. This line is exactly in between. So this is 45. This is also 90. This line is exactly in between. So this is also 45, this is also 45. This angle is 90, this line is exactly in between. So this angle is 45 and this angle is also 45 degrees. So if you look at the triangle ODE, 45 plus alpha is 180 degree. 45 plus alpha is 180 degrees. So 2 alpha plus 45 is 1. So alpha is 180 minus 45 by 2 degrees. So that is 67.5 degrees. If you convert that into minutes and seconds of arc, you exactly get 67 degree, 30 minutes of arc. Now the interesting point is at point B, the number of forces are less. So we'll first consider point B. Now, before that, when this turnbuckle is tightened, this force, tensile force P, for this point will be to this side and for this point will be to this side. And similarly here, for this point it will be to this side and for this point it will be to this side. The same P. Now, so S1, S2, S3, S4, S5, S6, S7, S8, they have been shown. For point B, S1 is to this side. For point C, S12 is to this side. And for point B, S8 is to this side. For point I, S8 is to this side. Is the same axial force S8, same axial force S1, right? So, considering point B where there are minimum number of forces, I have redrawn a diagram for you, then the free body diagram. This is same thing as your point B. Now that is shown here. This is your BC, this is your BI, this is your P, and this angle is also alpha. This angle is also alpha, as I explained here. This is alpha, this is alpha, this is also alpha, this angle is also alpha, and so on. This angle is alpha, this angle is also alpha, this angle is also alpha, this angle is also alpha, this is also alpha, so on. Alpha, 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 all these angles are the same alpha. So I have shown it here. Now, this angle is 45, I explained. This point is O, this point. So now at point B, I will draw the free body diagram. I will consider this as x-axis and this line, vertical line, as a y-axis. So that is shown here. So in the part BC, the S1 was pointing towards B. In the part BI, S8 was pointing towards B and P was away from the point B due to the turnbuckle. Now the value of alpha is found out, 67 degree 30 minutes. Now we'll take sigma x is equal to 0, sigma y is equal to 0. So if you consider sigma x is equal to 0, from here if you drop a perpendicular, from here to here will be your S1 cos alpha and this one will be from here to here, that is the side in front of the angle will be your S1 sin alpha. Similarly, from the tip of it, if you drop a perpendicular here and one perpendicular here, this one will be your S8 sin alpha and this one will be again S8 cos alpha. So S1 cos alpha, S8 cos alpha, I have to, let us shift this S1 to this side, this is your S1, this is your alpha. So the component of S1 to this side will be S1 sin alpha and this one will be your S1 cos alpha. Similarly, if you shift S8 to this side, S8, this being alpha, this is also alpha, so this one will be your S8 sin alpha, S8 sin alpha, and this will be your S8 cos alpha. Means S1 cos alpha, S8 cos alpha are in the same direction, that will be opposed by P, which will put as sigma y is equal to 0, and S1 sin alpha and S8 sin alpha and S1 sin alpha, this is your S1 sine alpha, they are opposite to each other. S1 sine alpha is along positive x-axis, S8 sine alpha is along negative x-axis, so they will be equal and opposite to make sigma x is equal to 0. So now look at sigma x is equal to 0 means S1 sine alpha is equal to S8 sine alpha. Let me redraw the diagram for this diagram again for you here for better understanding. This was your x-axis, this was your y-axis, P was to this side. This was your S8, from here to here was S8, which I can show it here as S8, making this angle alpha, and this was your S1. I can show it here because a vector can be translated parallel to itself, S1. This is alpha. So drop a perpendicular, this much will be your S1 sine alpha. Drop a perpendicular, this much will be your S8 sine alpha. So they must be equal and opposite to make sigma x is equal to 0. So sine alpha cancels, S1 is equal to S8. Now what about sigma y? The y component of S8, if you drop a perpendicular, will be from here to here, and that will be your S8 cos alpha. And if you drop a perpendicular from here, this part will be again S1 cos alpha. So S1 cos alpha, S8 cos alpha, they are in the same positive y-axis, so they are arithmetically added, that is being opposed by P. So to be in equilibrium, they must be equal in magnitude. So S1 cos alpha plus S8 cos alpha is equal to P. So for S8 I put S1, which we just proved, so 2S1 cos alpha is P. So S1 is equal to P over 2 cos alpha. Put the value of alpha, 67 degree 30 minutes, that comes out to, when multiplied with 2, gives you this much. So this can be rewritten as 1 over this times P. If you divide it with a calculator, this comes out to be 1.306 times P. It is a force of compression. So S8 is also of the same value, 1.306 times P, since S1 is equal to S8. Now if you look at the symmetry of the diagram, let me show you again. If you look at the symmetry of the diagram, the forces S1, S2, S3, S4, S5, S6, S7, S8 will be similar, will be same, by applying free body diagram at C, D, E, F, G, H, I, due to symmetry. So due to symmetry, your S8 is equal to S7 is equal to S6, S5, S4, S3, S2, S1, that is equal to 1.306 times P. All are compressive forces. From S9, S10, 11, 12, 13, 14, 15 will be equal to P, that will be a tensile force. So what is the conclusion? If P is equal to say 1000 Newton, P is equal to 1000 Newton, all these 1, 2, 3, 4, 5, 6, 7. That is these bars will develop the same force P as developed by the turnbuckle A in the bar BO. If each are equal to 1000 Newton, then 1000 multiplied by 1.306 will give you 1306 Newton is the compression forces developed in these bars BC, CD, DE, EF, FG, GH, HI and IB. What I mean to say is the compressive force along the periphery will be more as compared to these radial bars. these radial bars.